Hi, everyone. I wanted to take another second to introduce myself. My name is Shruti, and I am a process control engineer, part of the Control Suite team. So when you come into the office for the day with your cup of coffee and you log onto Control Suite, the first item you're going to access is the tree map. What you see here is a plant at a glance view of your process systems. Each large block is a separate process area, and inside those process areas are the loops that make up that unit. The size and color of the boxes are the process loops in that given unit. The color correlates to the health of the loop. So if you look at this reads a lot like a traffic signal. Green means that the loop is operating fine. Yellow means that the loop is running okay. And red means that there's an issue with that loop that needs your attention. The biggest payback will be fixing the loops with the red highlights. For this demo, we're going to use the data from the utilities process area, and we're going to focus on PC100. You can see that PC100 on the top left is a big square that's also red. So you know that there is an issue with that loop that requires your attention. By right-clicking on that loop, we can pull up the information on that loop. So once you've right-clicked on that loop, you can generate what's called a performance report. This is an example of what a performance report looks like. It gives us more insight on how to solve the issue with PC100. In the highlights, it has a more detailed analysis of what's going on with the loop. So it says here that the overall performance score was poor, that there was excessive variation in set point tracking, slow disturbance rejection, and that there's dominant oscillations detected. It also says to please check the tuning or look for periodic external set point changes or disturbances. And next to that, the highlights section, you can see that this loop has been given a performance score of poor. On the raw data section, you can see that the process variable and controller output are swinging too much for steady state control. And on the right, you can see that in the results breakdown, that the flowchart confirms all the information we just read. So let's explore this further to see if we can determine what is needed to improve the control of this loop. In the same report we began looking at in the previous slide, we also have a 4-gauge set that better defines what's happening with this loop. The first 2 gauges are set point tracking and disturbance rejection. The system finds that set point tracking is poor and disturbance rejection is slow. Set point tracking is when the process variable and set point are not closely matched, and disturbance rejection is the ability of the controller to react to unwanted external disturbances. The last 2 gauges help us determine where we need to concentrate our efforts. This loop is oscillating, and we can see on the right that there's no actuator issue. If a loop is oscillating, that causes a lot of instability. And it can be due to a number of reasons, including a bad actuator. But we know in this case that the actuator is not a problem. All this points to the need to tune this loop. But let's look at the data in a graphical form to see if our suspicions are well-founded. So here is a graphical overview of PC100. The output is in blue, the process variable or PV is in green, and the set point is in magenta. Based on what we're seeing here, the process is having difficulty holding set point, and that means the process needs tuning. A bump test was made as shown in the highlighted section in the middle part of the graph, and what we can do with this is highlight the highlighted section and right-click to display a variety of options. We can click on Loop Tune in the red box there. And if you have Data Park, you can actually install the Control Suite package on top of Data Park, and Loop Tune and Loop Performance Report will come with that. So step one, when you open up Loop Tuner, this is what you're going to see. This gives us a model of the process and gives us the ability to make changes to the loop in an offline mode. Some points to note here is that the system has pre-built algorithms for almost all DCS and PLC systems in use today. When you select your DCS or PLC system from the menu, the tuner knows what engineering units each system will need. It then allows you to make the changes offline to ensure that whatever changes you make is done offline and won't interrupt the process. We know each system is a little different, and because of that, in the model builder, you can change your model to better suit your process. And here you can see that the existing tuning parameters are listed and represented graphically. Step 2 is the model prediction. So here is what the model prediction looks like in Control Suite. This shows how the actual process correlates to the model. You can see at the bottom graph that the model from our previous slide and the actual data from the process are a pretty good fit. So step 3 is to tune our loop. There are many different options that you see here. The first thing you do is to select your DCS or PLC platform from the drop-down menu on the top left. Then you can add your output and process variable span under the DCS or PLC type. And you can also modify your controller type, PI or PID, by clicking on the radio dot. After you've customized your settings to reflect your system, you can tune the process by clicking Tune on the bottom right. You can even make changes to the tuning as every process is different, and you can customize it to your needs. As you can see, this offers you all the tools you need to modify and confirm and test your ideas. So when you've completed the tuning, you can generate this report. The person responsible for your control system can install these new parameters knowing it's not going to cause any kind of process upset. Juicy, can you please change the slide?
Okay, I was losing a connection for a second. I was about to ask that. So I didn't hear you for last 30 seconds, but yeah, you wanted to change the slide. Are we okay?
This is the after picture of our tuning result. So you can see on the left, this is what our process looked like before tuning. Our loop is oscillating quite a bit. And after we've input our new tuning parameters, on the right you can see what it looks like. The process variable has settled out and the controller output is no longer oscillating. Now you can generate your performance report again. And you can do this at any time. The performance report is always there and you can generate it as many times as you'd like. Here's what it looks like after our tuning. You can see that the performance score is excellent now. And in our highlights section, it says that there is acceptable set point tracking, no significant oscillations. And at the bottom, it even says, even though the disturbance rejection shows signs of aggressiveness, the lack of dominant oscillations suggests it's not affecting our performance. The gauges are also reflecting our positive change made to our loop. Set point tracking is good. Disturbance rejection is good. And our oscillation detection says there's no significant oscillation. And we have no actuator issue. So we can generate this report, hand it to our management team, which will highlight this change and the potential cost savings generated. The next day, when I open up my performance chart, I can see on the bottom right that PC100 is no longer an issue, and we can see that that block is green now.